what we're today going to do, finally, which I promised earlier, but I was lying apparently, is to leave this first main block of topics, namely symmetric algorithms. We are through, we are done with symmetric algorithms. That means, this was October 2010 when the semester started. We're here, okay? So we're done with symmetric algorithm. Today, a completely new world of cryptography opens up to you, namely public key cryptography. It's part of cryptography. The methods are pretty much entirely different. So it's, if you just joined, if you just joined the program, if you missed the first 4 months or so, essentially no problem. Everything that we're going to do today is more or less unrelated to the last 4 months, which is good and bad, I guess. Okay, so if you were sleeping most of the last 4 months, no problem. It's your chance for a fresh start. What we are going to do today is not actually doing the cryptography itself, but we have to do mathematics. There's one many big difference between symmetric and asymmetric cryptography. And public key is, by the way, public key cryptography is the same as asymmetric. One of the big difference between asymmetric and symmetric ciphers is that they're all based on heavy mathematics, namely number theory. So what we're going to do today, which is only happened one more time till the end of till the summer, is that we are doing for 90 minutes, we're just doing math, new mathematical concepts. And probably some of you might have seen the algorithms we're going to introduce. Namely, we start with the Euclidean algorithm. What we are really interested in, and as the hard part, is the middle part, so you have to be awake, okay? You can sleep in the beginning, at the end, be awake in the middle here. We're going to do the extended Euclidean algorithm, very important. And at the end, we're going to have some theorems. Let's start. So first chapter of today is the Euclidean algorithm. Who knows the Euclidean algorithm? Who did that in school? 1, 2, 3, all the people in the master's program. Could you raise your arm again so that I can see him? Oh yeah, it's almost a quarter of the students. This is impressive, or maybe a third. That's good. Okay, so what does the Euclidean algorithm do? What does it compute? I just saw 1/4 of the hands going up. Yeah. Yeah, GGT, greatest common divisor. Okay, so what the goal is, what we're going to do, and this is going to be very important in cryptography and public key cryptography. The goal to start with is, given 2 numbers, and if you say numbers, we always mean integer numbers, natürliche Zahlen, given, and we call them R0 and R1 for the rest of today. Okay. So if somebody gives you 2 integers, we would like to find the GCD, or GGT in German, GGT. Okay, so we want to find the greatest common divisor. That means the greatest integer, the largest integer that divides both numbers. Okay. Let's start with an example. R0 is 27, R1 is 21. Any idea what the GCD is here? Can anybody do that mentally? Who has an idea? Who wants to? Yeah. Very good, it's 3. So what do we do? How do we get? How did you do that? Können wir in Deutsch machen. Was? Primfaktorzerlegung. So he does a prime factorization. Very smart idea. So you look at 27, how that factors, and this is 3 times 3 times 3, and then you look into the factorization of 21, which is 3 times 7, and then here you look at the common prime factors, right? You see the 3 here. And this is in fact the greatest common divisor. Okay. This is a great method. It has this charming drawback. It doesn't work for large numbers. And in cryptography, we're always working for with large numbers. Okay. It's a very intuitive method. It's not very complicated. It doesn't work in practice. Okay. That's the first thing we want to learn. This naive method of just looking at the prime factorization doesn't work because the numbers we're looking at are so big we cannot factor them. Okay, 1000-bit numbers in RSA nowadays. We cannot factor 1000-bit numbers. It doesn't work. So the question is, are there faster methods available? And surprise, surprise, there is a faster method available. This is the Euclidean algorithm. Okay. The idea of the Euclidean algorithm maybe let's write that down. Question is there a faster? And if we say faster, we mean less complex, right? In computation, is there a faster method? Okay. And the idea is, and again, we're talking about large numbers. If you have small numbers, it's not a problem. We can factor, you know, sometimes mentally. Right? Kopfrechnen, that's what we just did. What we're trying to do, this is an iterative process, namely you start with large numbers. Again, your web browser sometimes has to do that when your web browser is establishing a secure connection to amazon.de. The idea is to reduce the problem dealing with large numbers, with two large numbers, to two numbers that are a little bit smaller. Okay, and then we do that once. And then we take the somewhat smaller number and reduce them again, we get somewhat smaller numbers. And smaller numbers and smaller numbers and smaller numbers. That is the idea. Without and of course, doing this reduction without factoring every time, right? So this is a reductive algorithm, reduces problem with large number to a problem with smaller numbers, and then we try to do that over and over again until we end up with really, really small numbers so that we can do that with our pocket calculator. That's the idea. So, and there is a very simple reduction step at the very, very heart of the Euclidean algorithm. So we start with GCD of, again, two numbers, R0, R1. And this is our symbol, okay? This is in no book except my book, okay? This means O, okay? Means O, okay? Surprise, this means surprise, okay? So this doesn't mean big O, okay? So this GCD is the same as the GCD of R0 reduced modulo R1. So we replace R0 by a reduced version of R0. By a reduced version of R0. And R1 stays the same. Okay. And then what we usually write is you can swap the operands in the GCD of okay. Proof is in the book, in the textbook. And Dayan is also going to do that in the Übung, right? In the help session. Okay, so next week he's going to show you that. It's not complicated, but I don't want to spend some time on that because there are other important things to spend time on today. Okay, it's not that hard to see. And we're going to do, as always, we're going to do examples. So how can we do that now? This is, again, this is just one way of reducing a problem with certain numbers of a certain size to numbers with a somewhat smaller size. Okay, and let's look at an example. And let's look at the example we did before, GCD of 27 and 21. And let's look a little bit at this graphical representation, what's going to happen here. So we imagine 27 as a number that is this long, 27 centimeters or whatever, right? 27 Castile, whatever you want to do. You don't have to do you don't have to be that exact, okay? It's not worth it. So, and then we have 21, which is a shorter box, obviously. Is that right? Okay. So, what this reduction tells us is that the just GCD of the original problem can be reduced to, does anyone know what is, maybe let's write it down, 27. What is this here? 27 more 21, what's the remainder? 6, very good. So this is the GCD of 6,21. Okay. Where is the 6 in this diagram here? It's this part here, right? This is 6. This is 21. Okay. So this is only thing we did here, visualize, very baby-ish, very graphical, very obvious. We looked at an example for this. Okay, this is not an algorithm. Okay, this is just one formula exploited. We don't even have a proof for this formula. We just believe us. Okay, so now let's turn that into the algorithm, and I already hinted on that. We do that now repeatedly. Okay. Again, we started with this long number 27 and 21. What this tells us now, we can reduce it to a smaller problem. So what we're going to do now is we pretend there wasn't even a problem with large numbers. We just say, well, the problem is only GCD of 21 and 6. Okay? So forget what we did before. We say this is the original problem. Okay? It's not the original problem, but we can pretend that. And then we do the same trick again. So now we have to draw 6, which is rather short. It's maybe this long. Okay. And again, what we're looking at is the remainder of 21 if you divide by 6. So how do we do that graphically? Well, you look at something like this. You have 6, 6, 6. And what's left here? Can anybody laptop open? What is the remainder here? It's 3, right? Exactly. So you take 21 modulo 6, there's a remainder of 3, so this becomes GCD of 6,3 or 3,6, and then you swap the operands. Okay? This is good. And now it's about to get boring, right? Now you do the same step again. You say, we're not interested in solving 27 and 21. We're not even interested in this. We have now really small, nice numbers, GCD of 6,3. And this is a special case. This is a degenerated case. This is an extreme case. Why is that an extreme case? If you look at 3, what is the remainder here? 6 divided by 3, 0, right? And what is the GCD here? It's 3. If you have this extreme case, that's a smaller number, that's a larger number, is a multiple of the smaller number. The GCD is the smaller number, right? You know, if it fits in without remainder. So here we have this case. You have 3, 3. And normally, you know, here we should do that this way. This was always a remainder. There's no remainder here, right? It's 0. So we're there. And at this point, remainder is equal to 0. This tells us we are done, okay? We terminate the algorithm. What you're going to do in your C implementation later on, or your Java implementation, you're going to do this next step. That means you are going to compute the remainder. And before we had the remainder of, we computed 6 and then 3. You know, we computed this remainder, this remainder. Here you will compute a remainder of 0, and this tells you we are done, okay? You can write that, if you do that with pencil and paper, you can write that in the following form. You start with 27. And what you're going to do, and I think we did that in the first or second lecture when we introduced model reduction. We had this canonical way, the systematic, basic way of writing a model reduction. And what we did is, you know, we have 27, we want to reduce that module to 21. So what we did is we say this is a multiple of the smaller number, right? And this is a quotient here. So you have to fill something in here plus the remainder, okay? What is the quotient here at this point? What do I have to write down here? 1, exactly. This is 1. And there's a remainder of 6, what you see before, okay? This is kind of the first step that we did, okay? And now we do the same spiel. Before we did it with 27, 21, now we do it with 21 and 6. Do you see there the second line? Again, you have to compute the modeler, so you can, this shifts to the left. So you write this 21 is equal to multiple of 6. You know, you have to put the quotient here plus the remainder. What's the quotient here? Very good. What's the remainder? 3, yeah. Okay. Now you do it again. Instead of dealing with, originally we dealt with 27, 21, then we replaced, you know, we shifted them over. And now we're dealing with 6 and 3. You get a quotient, a multiple here of 2, and the remainder of 0, okay? And what I would like you to do is now you get 3 minutes to do this here in your heft, okay? Without me. You're on your own, okay? I have my 3 minutes break. Try to do it in this way here. And we're going to use this example for the rest of the lecture, so it's really good that you do that now, okay? Please. This is what I mean. Starts this way, okay? And don't use pocket calculator or your iPhone or whatever pocket calculator, right? The numbers are really nice. You can do them mentally. 262. Any results? Is anybody done? 7 is very good. 7 sounds good. Okay. So this 3 times 301 plus 70. Again, you shift them over. Here you see that the 70 fits in 4 times in the 301. Gives you a remainder of 21. Now you operate on 70 and 21. The 21 fits in 3 times. Gives you a remainder of 7. Okay, so. And things are going to get more complicated in about 5 minutes. Okay, this was pretty nice. What we're going to do that pretty systematically, we need names. Okay, and these were our original variables. They were called R0 and R1. This is the first new remainder, the first remainder that we computed, the first new number. So this we call R2. You know, now you're operating on R1, R2. The new remainder becomes R3. This becomes R4. And then R5 would be 0, but because this is a trivial remainder and the algorithm is really done, it's kind of a funny thing because this tells you the algorithm is done. And the solution, if you wish, you find one line above, one step earlier. The last, if you hit a 0 here, the solution is the last remainder you computed before the 0. Okay? This is the 7 here. Okay? Very good. So, now we're done with the first part of the lecture, which was important, okay? And the second part, I know it takes us probably 30 minutes or so, do the extended Euclidean algorithm. Please pay attention, okay? This is no fun if you're going to do that Wednesday evening next week, okay, to do the homework assignment. You don't want to do that on your own, okay? You don't want to learn that algorithm on your own. Okay, so chapter 2 of today's lecture is the extended Euclidean algorithm. The start looks quite similar. Again, given our 2 integers, this is not very exciting. You have R0, R1. What we want to compute is, there are kind of 2 things, really 3 things we want to compute. The first thing is exactly what we did so far. We want to compute the GCD as before. And this is actually what we did so far. This is easy to understand, but this is not the stuff you really need in cryptography or number theory often. What we do want to have is this Linearkombination, a linear combination of R0 and R1. And obviously GCD is not R0 plus R1, right? I mean, you can check that here. What was the example? You know, R0 plus R1, what is that? 1274. This is not true. So what you need here are coefficients, namely a coefficient we call S, and a second coefficient that we call T. And what the extended Euclidean algorithm gives you, computes, is the old boring GCD, you know, which we just learned 5 minutes ago, but it also computes these 2 coefficients, namely coefficient S and the coefficient T. Okay, and now the big question is how, right? Well, the first thing is easy to compute. This is this stuff here, right? Left-hand side of the board, okay? So there's still the plain Euclidean algorithm is still hidden in here. But in addition, we have to compute S and T, and it turns out this is a pain in the neck. Okay, these are not that easy, but they're doable, and that's why I told you please pay attention. And we together we derive ways of computing S and T. Okay, and kind of the different ways of explaining that. And my way is somewhat peculiar, somewhat special, and please pay attention for the first 2 minutes, which is the basic idea. And I'm always looking for a better way of explaining that and haven't found it, okay? So the idea that we are following, which is already a certain intellectuelle Leistung, okay, just to get the principle of the algorithm, okay? So first we basically doing what we did here. So we basically compute the regular Euclidean algorithm, compute regular, and it just abbreviates it with EA, extended Euclidean. Euclidean algorithm, so this is the boring one. This is left-hand side of the blackboard, okay? That's what we're doing here. As before, you start with the GCD of R0 and R1. And how do we compute that? You know, you always look at this representation. You say R0 is a quotient times R1 plus a new remainder R2, okay? Oh, and we give number. We are going to use the quotient. So far, we didn't needed the Q's. We're going to use them from now on. And now comes the important thing, and I hope you can follow what I'm telling you now. The only thing we do extra in each of these iteration steps, we take the new remainder, the remainder we have newly computed, which is R2 in this case, right? And we write that in a special way, namely we write R2 in this way here, namely as a multiple of R1, multiple of R0, and a multiple of R1, okay? And this is easy, this is simple algebraische Umformung, you know, x auf eine Seite bringen, this stuff. This we can do with regular manipulation. And of course you need, again, coefficients here. You need S and T, and we give them names. We call them S2 and T2, okay? And here actually, if you have to do that, you can do that right away, and we're going to derive that in a minute, okay? This is easy. From this formula, bring that in this form, okay? And now, we continue. We do the next step would be computing the GCD of R1, R2, and what we're doing, again, you derive such an expression. So you look at how often does R2 fit into R1? This is Q. Which was, the second line was 3 here in this example, right? So you get a Q plus, and this is maybe more important, you get a new remainder R3, and now you have to wake up, okay? This is what we're going to do. R3 is also written in this way. And hopefully we can do that. So again, you express R3 in terms of the original, the input parameters, right? You start with R0 and R1. Okay. And how we do that, this is kind of this is the hard part. How can we actually write it this way? This is, it's going to be the next 2 blackboards. Okay, we're going to show you that. But why is this a good idea? What happens at the end of the algorithm? At the end of the algorithm, the last iteration, and I call them L for last, right? We have RL minus 1, RL minus 2. It's actually the other way around, I'm sorry. This is a larger number. Okay? So what we do, QL minus 1 times RL minus 1 plus RL, okay? The next iteration, the remainder will be 0. So this is the final equation that we compute. This is dot, 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 right? Dot, dot, dot. So what's happening here is now, again, somehow, right, we will be able to write RL in this way, okay? That means we have SL plus TL, okay? And here, if you want to write that down, in the last line we have RL minus 1 is QL times RL plus 0 here. You get the 0 here. So this is the last RL is actually the last remainder you computed, okay? And now it's really the hard question, and again, I hope my explanations work. Does anyone know why we won? If you can do that, why have we achieved what we want to do? Why are we there? Does anyone know why? What is this RL here? Does anyone know? That's the GCD. That's the end of the algorithm, right? This is the 7 here. Okay? This is the last remainder that we computed. This is the GCD. But GCD of what? Of the original problem of R0, R1. So what is S and T now? Yeah. Exactly. The last S and the last T value that we computed are the final S and T values, right? So this is equal to, this is even. C'est ça, okay? This is the rational, the rational behind the algorithm, the idea, the principle, okay? So, again, you do the regular algorithm. I assume it looked like most people in this room got this right. So you do this as before. The only thing, in addition, you have to always compute this funny expression here, and it's not clear that you can do that, but you can actually. So now what we have to do in order to turn the Euclidean algorithm, this is this here, into the extended Euclidean algorithm, come up with ways of computing this here, okay? So really the question is, how do we do this stuff? And this is what we're going to do now. Oh, by the way, I have to jump back. This is a bad teacher. Before I started the second chapter, Extended Euclidean Algorithm, we did this here, right? And what I wanted to show you, I'm sorry, is on page 162. This is the Euclidean algorithm pseudocode, which is pretty close to C coding, okay? So you go in with R0 and R1. This is a loop that terminates with this condition here, right? This is what we had. If Ri is the new remainder you compute in every iteration. If the remainder is not equal to 0, you continue the stuff. Otherwise, you terminate, and the last remainder, last non-trivial remainder you computed is a solution, okay? So it's essentially like 2 lines of code or so, and this is what you did before, okay? Do you have already C? Do you have the C class already, the C lecture? Programmierung in C? Do you have that already? Next semester, is that right? I think, yeah, next semester. In C, there's this inline commands. You can, I had once a student who wrote the entire Euclidean algorithm, and I'm not joking here, in one line. You can put that in one line, actually, with an implicit if statement and stuff. Pretty cool, okay? So this is very, very simple. Again, switching back to the second chapter, you know, we're stuck here. How can we do the right-hand side of this, okay? And what we're going to do is, we're going to stick with this example. That's why I told you, please do it. And I'm going to do it for you on the blackboard now. So again, we have the same numbers. We have 973 and 301, 301. And what would we would like to do is we would like to write it in this way times and we do know the GCD from here, right? Because we all did that before. So I can maybe write that down. So this we already did. This is the regular Euclidean algorithm. That's the GCD. What we don't know what S and T is, and this is not that obvious, okay? But now let's try to follow this master plan, okay? So here we have I, which is the iteration counter. And this is one thing in this Euclidean algorithm, because we call this R0 and this R1, so 0 and 1 are taken already. So the algorithm starts with this Zählvariable, you know, the counter set to 2, okay? Very confusing, I know. But it makes it easier. So what you do here is you take 973, and again you decompose that into multiples of 301, which is 3, and I'm just copying what's over there, plus 70, okay? And here are the variables. This is R0, this is R1, and this is a new remainder we computed, R2. So what we said above, and now we have to start thinking. We want to R2, which is 70, we want to express it in this form here, okay? So what we're looking for is a multiple of 973 plus a multiple of 301. So I'm looking for two coefficients. What do I have to write here and here? And we can get that out of this equation. This is really easy. The first time is easy. What do I have to, 70 is equal to what? What do I have to write down here? This is 1, right? It's 1, and you know, it's just my notation to stress, you know, the brackets, eckige Klammern to stress, this is a coefficient. What's going in here? Anyone know? Looking at this here. Auf die andere Seite bringen, right? So it's -3. Can you read that? This is supposed to be -3. Okay. Wasn't that hard, okay? It's getting more difficult. So now let's do the second iteration, which the iteration counter equal to 3. So now we go in with 301 is certain multiple of 70. How often does the 70 fit in the 301? We saw that before 4 times, and I think most people hopefully did that before. And we get a remainder, a new remainder of 21. So what? And this is a remainder of 3. And again, the rule is always look at the new remainder and express the new remainder in terms of R0 and R1, okay? So what we're trying to do, probably just use this equation that worked before, right? Just do algebraic operation on this reduction equation we just had. So what do? Is we we say this is 301 minus 4 times 70. Okay. Now you look at this equation, and now you have to start paying attention. This is the first time really we get into the function, the mechanics, the details, das Getriebe of the algorithm. The 301 is good here, right? Because, t times 301, so this is our 0. What is bad here? A 70, right? We want to have a multiple of 301 plus a multiple of 973. So how do we get rid of the 70 here? Very good. This is the answer of today, the line above, okay? Why is that? You replace the 70 with this expression, and here you find nicely 70 is represented by 973 times something plus 301 times something, okay? Einsetzen. You go one line up and you substitute. Gonna fit that in here. Orange, okay? Important. Orange means important, okay? So 301 we keep untouched. Minus 4 times the stuff above, and now I skip the brackets. It takes too long. Minus 301, okay? And now we do a reshuffling, or ordering would be. Now we order, and again the multiple of 900, I can write it down here. 973 plus I'm looking for this. So what is the multiple of 973? How often does the 973 occur in this equation here? What do I have to write down in here? What do I have to write? Minus 4, very good. And 301, how often is the 301 in this equation? What's the coefficient here? 13, namely minus 4 times minus 3 is plus 12 plus 1 times, right? It's 13. That was fun. Okay, let's do that again. And there aren't that many iterations, don't you worry, okay? Again, first we do the boring part, the old, Euclidean algorithm, which we've known for 20 minutes now. So this is 3 times 21 plus a remainder of 7. And this is R4. And again, you do the same thing. You try to, the goal is R4 is a multiple of 973 and a multiple of R301. We do the same thing. We start with this equation. We just generated this equation. Let's start with this equation and umstellen, right? Getting R4 on one side of the equation. So we get 70 minus 1. So now we have, before, remember, we had one problem. 301 was okay. The 70 was bad. Now things look bad. We have a 70 here, and we have a 21 here. How do we deal with that? Again, what's it? That's line above is halbe Miete, half the rent. But the line above doesn't save us completely. What else do we need? Yeah. The line above and the line above, right? So what the 70, the 21, this is exactly what he said. The 21, we can replace from here, and the 70 we get from here. That means, and this is the general rule, go back one line, go back the second line. This has all the information you need in order to succeed. Okay, so 70, this is 1 times 70, so we take this is 973 minus 3 times 301 minus 3, and now we go into the into 21, which is this line here, which is minus 4 times 973 plus 13 mal 301. Okay, so actually a more exact what I should have done is it's no big deal, don't panic. So this 21 you get from here, and this 70 you get from here. Okay. No, this is wrong. Right? One line up, right? Bad professor. Is this better? Yeah, I think. Okay, so now we have to reordering of the coefficients. So we're looking for the multiples of 973. What do we have to write down? This is 1 times plus 3 times 4 is 12, 13 times. Is that what I have? Yeah. So this is 13 times 973. And now we have to look at 301. This is minus 3. Minus 39 is minus 42. Is that, yeah. Minus 42. Okay. And so why is that so cool? Why are we done? Because our 4, remember here, if we continue, next time we would get 0. So what the regular Euclidean algorithm tells us, the 7, which is the last remainder we computed, is a GCD. So this is the solution of the problem. So our 4 is the solution of the regular Euclidean algorithm. And by the way, our 4 can be written in this way. So by the way, 7 is 13 times 973 minus 42 times 301. Okay. What? So I'll tell you in a little bit. No, it's short answers, I'm going to do that in 10 minutes, is we can compute inverses, inverse modulo p. We can't do until now. Okay? This is a very, very hard, very computational, intense step to divide. So far, I don't know whether you're aware, we cannot really divide modulo p. Arithmetically we can, but not computationally. You don't know how to divide. The only time we needed that with the affine cipher, you always did brute force to find an inverse. You just tried all numbers. This is a way of really computing it. But it's a good question. So why do we care? Because we want to compute. Okay, we want to divide, and I'm going to show you in a minute. Okay, so well, this worked nicely for this example. The question is, how does this work with other numbers? Okay, and you can actually turn that into a nice algorithm. In general, we have the following situation. You're inside the algorithm, after 10 iterations, or maybe it's the second iteration, but let's assume you're there after 10 iterations. And what you did after 10 in iteration, let's say iteration number 10, you computed Si minus 2 times R0 plus Si minus 2 times R1, T, I'm sorry, Ti minus 2 times R1, right? So this is the right-hand side. So you have this line, and then also given is the solution to the next iteration. This is Ri minus 1, which is Si minus 1 times R0 plus Ti minus 1 times R1. Okay? So this is given, you know, it's an iterative algorithm. You're in the middle of that. So always the question is, how do we get to the next step? What's happening in the next iteration are really two things. The regular Euclidean algorithm, this is what we have on the left-hand side there. The regular Euclidean algorithm gives you this equation, Ri minus 2 is equal to Ri minus 1 times Qi minus 1 plus, this is the new remainder Ri. So this is what we wrote on the left-hand side. So now we're going to do what we always did on the right-hand side, you know, with the yellow lines, this part of the blackboard here. Please pay attention, this is the best part of the lecture. Stop playing cards, pay attention, at least for this moment. You can go back, but for 1 minute, please, please. So what you're going to do here is what we did for this one example, I do in general now. This is the new remainder you just computed. So and now you take this new remainder and rewrite the equation above. You say, okay, Ri is Ri minus 2 minus Q times this here. So far, so good. But what we want to have is Ri is equal to something with R0 and R1, okay? And this is what we said before, you know, the golden rule is go back one line and go back another line. And this is exactly what we're doing here. The Ri minus 1, minus 2, you get from here, and the Ri minus 1 you get from here, okay? Again, you substitute, ist nur einsetzen. And then we get Ri minus 2. I'm just substituting this whole thing here. This is Si minus 1 times R0 plus Ti minus 1 times R1 times Ri minus 2. So this is Ri minus, oh yeah. This is minus 2, danke. So this is this here, right? Minus Qi minus 2 times this here, okay? Ri minus 2 we get from the second line here, so you have to, it's a lot of writing, a lot of indices. We copy the second line. This here. Okay? And that's it. Now you have to do reordering, and there are many terms, blah, 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 blah. If you reorder that nicely, you get the expression Si minus 2 minus Qi minus 1 times Si minus 1 times R0. So we extracted all the coefficients that belong to R0. And here we extract all the coefficients that belong to R1. Now there's a lot to follow here. And what kind of simple name do we give to these brackets here? Zu dem Ausdruck in den eckigen Klammern. What is the name for this? What's the new name? Exactly, this is Si. This is Si times R0. And now, really difficult, what is the name of this expression here? This Ti. Okay. So, and I don't know whether this is clear, and I know I'm using a lot of colors these days. So, this is not only yet another example, this is the general formula from computing Si, given what? Given the previous Si, the previous Si, going back, this is going back one line, going back 2 lines. And what else do we need from the current iteration? This Q value, right? This is what we get from the regular Euclidean algorithm. Similar with T, you need the previous T value. You go back 1 line, you go back 2 line, the previous one, and the Q value, the quotient you just computed. Okay? And that allows you to compute the next S. That means we have very, very nicely recursive formulae. That's the fancy plural of formula, or formel in English. Recursive formula for the S coefficients, namely Si is I minus 2 minus Qi minus 1, Si minus 1, and exactly the same formula holds for T. Okay, and this holds for I starting at 2, so 2, 3, 4, 5, and so forth. This is exactly what we've seen here. This is exactly what we derived here. Okay. So right now, this time there was no hand waving. We actually derived an algorithm here. There's one thing missing. Let's try to plug in numbers. It has to do how do we start the algorithm. So the smallest I value is 2. So the first S that we want to compute is S2. But then we need, at this point, S0 and S1. And we don't have a formula for S0 and S1. So and for this, I give you, these are the starting values, the initial values. They're part of the algorithm, namely wobei S0 is 1, S1 is 0, and T0 0 is 0, and T1 is 1. And this is a time where I'm skipping. This is not clear where these starting values come from. I think there's a homework assignment in the book. I don't know whether we give them to you. This is not completely, it can be done, it's not completely easy, but you can do that, okay, where these initial values are coming from. This is the recursion you need. If you look in the book, there's a, how do you turn that into an algorithm you want to program, or you have to program? There's the algorithm up there. Blah, 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 initialization, boring, 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 boring. What is not boring are the line 1.4 and 1.5. What you see here is this here. Okay, so at the heart of the algorithm, are the computations of the S values here and the T values, okay? What you do before here, this is a regular Euclidean algorithm, line 1, 2, and 1, 3 is just a complicated way of computing the quotient, okay? Quotienten berechnen, okay? And as you see, at the end of the algorithm, your final S and T value are just the last values from the algorithm, from this iterative algorithm you ran. So the hard part is over. You can go back to sleep. You can start playing cards again there, this line. You can start again. So what I'm going to do now is, this was the really hard part of the lecture. It was an excellent question before. Why? You know, why? I mean, this problem, where did we start? What's the first board here? Why do we want an S and a T? This seems like a pretty artificial, not very useful problem, right? But it's super important. The opposite is true. And now what I'm going to show you is really, really easy, but very, very important, namely the main application, Hauptanwendung of the extended Euclidean algorithm is computing of inverses, also Inversenberechnung, inverses modulo n, call that modulo n. And this is really easy, okay? The problem is, Problemstellung is, you would really like to know what the inverse of A is. So given are, interestingly enough, given are two numbers, namely A and the modulus. Two numbers, and this is what we have too, right? Given are two numbers, so that's, maybe that works somehow. So how is an inverse defined? An inverse is defined such that the inverse of A times A itself is equal to what? What do I have to write down here? Very good. Definition of the inverse. Okay, so we want to construct this equation. So what you're going to do now is your plug A and N, that means the element you want to invert, and the modulus into the extended Euclidean algorithm. Okay, means you compute GCD. N is a larger number. That's by convention we write that on the left hand. So we write that first, and A. Do we know what the answer is? What the GCD of these two numbers is? It's 1. And why is that? Why do we need a 1 here? Yeah. In order for the inverse to exist, we have this GCD condition, right? We did that in the second lecture. If there is an inverse of A, the GCD must be 1. Okay, so this is not the hard part, obviously, right? But then we do all the stuff with these equations and going back 1 and 2 lines, blah, 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 the extended Euclidean algorithm. And the extended Euclidean algorithm gives us S and T. It's okay. And I write the 1 here. That makes it a little nicer for explanation, okay? Everybody with me? So again, the extended Euclidean algorithm gives you S and T. And why is that really cool? And now the next step is the nice one. You have this equation over the integers, and now you say, well, let's take this equation modulo n. You can do that, right? This is an integer equation, it holds. So you reduce this part modulo n and this part modulo n. Well, we don't, 1 modulo n stays modulo n. What happens S times n modulo n? What is that equal to? Nope, not S. S was a good try, but it's wrong. 0. Yeah, what's the remainder of n divided by n is 0. So this doesn't cancel out. This is 0. So what's left is T times A is equal to 1 modulo A. And now you should see the light, okay? What is the solution? What is the inverse of A? You see that? Compare, really hard, really difficult. Compare this equation with this equation. What is the inverse? T. This is cool. Yeah, thank you. Okay. That means this T parameter, that means the parameter of the smaller number in the extended Euclidean algorithm is the inverse. The parameter, or coefficient, we called it before coefficient, the parameter T of the EEA, extended Euclidean algorithm, is the inverse of, if you go back to the Euclidean algorithm, of R1 modulo R0. So we spent 70 minutes on a way of finding a method, and it's painful, it's a lot of work. But finally, we can compute inverse. That means we can actually divide. All the other operations are easy. What are the other operations? Addition modulo n is, it's plain old addition with modulo reduction. Subtraction is the same. Multiplication is the same. Multiplying a times b modulo n, you just do a regular integer multiplication into your reduced modulo n. That is easy. We didn't have a solution until 5 minutes ago for dividing. Division is, multiplying with the inverse. We didn't have a way of doing that, and this is completely different. This is, in order to divide, you have to run this whole algorithm. That means there's much, much more work involved in dividing modulo n than with, let's say, multiplication, for instance. Okay? And of course, in cryptography, we have normally algorithms that also require division and computing inverses, and that's why we've done that. Your web browser, for instance, does that. If you establish a secure connection with your web browser, this stuff is active. If you have a new electronic passport, an electronic national ID card, deutschen Personalausweis, with a chip on side, there's also public key happening. This is one of the things that are happening here. Okay, so this is really very real, and what you're going to do from now on, about every other week, so every 2 weeks, I'm going to introduce a new public key algorithm. There's 3 or 4 main algorithms we're going to do here, 5 almost. And in almost all cases, as you can imagine, you write down an algorithm, this is how you encrypt, or this is how you compute a digital signature. And very frequently, I will say, oh, we have to divide, or oh, we need an inverse. And what that really means, if you want to do that in practice, every time you see a division, every time you see an inverse, you have to run the Euclidean algorithm here, okay? So every time you have to run essentially this box up there in pseudocode. Okay, you're going to hate the Euclidean algorithm, right? It's very hard to do with a pencil of paper and pencil. So the good thing is we're done with the hard part of the lecture. And now we have a collection, I think 3 or so theorems. That means results from number theory, which we're going to present without proofs. They're important, okay? But they're more or less facts that I give to you. I'm not going to prove that because it would require another 90 minutes or 120 minutes maybe. So, and there's 3 different theorems I want to present to you. Some theorems and such. Also auf Deutsch einige Theoreme und sowas. Ja, weil the first thing is not a theorem, right? So that's why. Okay. The first, so maybe let's call that 3.1. This is Euler's phi function. Euler's phi function, Eulersche phi-Funktion. Okay. So what is that? And this is actually it's going to be very, 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 very important next week when we talk about RSA. RSA, in turn, is the most important public key crypto system. So this is an important little, whatever function I'm going to tell you. For some reasons, which are absolutely not clear at this moment, but they will be clear in 7 days from now. For some reason, it's in cryptography very interesting to solve the following problem. Namely, you have Zm, that means a set of integers starting from 0, 1, up to m minus 1. And what we are, for whatever reason, which seems very strange at the moment, for whatever reason, you would like to know, you have m numbers here, 0, 1 to up to m minus 1. You would like to know how many of these numbers are relatively prime to m. That means, you compute 0 and m, which is, by the way, m. And then you compute 1 and m, you get some result. You get 2 and m, you get the result. So you get results, okay? And you're not interested in the results per se, but what you're interested is how many of those have as an answer 1 here. We say relatively prime, relatively prim, 2 numbers, if GCD of these 2 numbers is 1, okay? Now you're interested how many of these m GCDs have as a result 1. You don't even want to know which ones, but just how many, okay? And this is that's the definition in the book. Okay, so this is a more formal definition, which I just explained with words. The number of integers in that m, that means out of m numbers, how many that are relatively prime to m is denoted by phi of m. This is Eulersche phi-Funktion. What is this? Let's look at an example. Okay, So what you need at this point here is a definition, right? Which is number definition 631, 6.3.1 from the book. Okay, I'm not going to write that down here at this point, right? It's on the wall and you all have the book. But let's look at an example. Let's look at m equals 6. That means z6 is this set of integers. And now run through all elements. So we compute GCD of 0 and 6 is actually 6. 1 and 6, 2 and 6. 3 and 6, 4 and 6, 5 and 6. What is the GCD of 1 and 6? Why don't you do that? I give you 60 seconds, okay? Why don't you compute all these GCDs here without pocket calculator, okay? Okay, and now we're looking for those results that are relatively prime, which are this here. This is the result, this one. So this one, and that means we say 1 and 6 are relatively prime, and 5 and 6 are relatively prime. Okay, so and I just mark them with a star. And what Euler's phi function does, it counts the stars. Okay, you look at this, you count the stars, 1, 2, and therefore phi of 6 is 2. C'est ça, that's it, okay? Very, very important cryptography, very important for your web browser, okay? Very important function. So, and now you know that there's a crypto system RSA. Again, we're going to do that next week. And if you want to break RSA, you have to factor. Who has heard about this? Is cryptography and factoring has something to do with each other? Who has heard that at some point in your life? About 22% of the people, 30% of it. Okay, so, and this is at the very heart of that. Namely, as you will see, RSA, which is in every web browser, it's the most widespread public key crypto system, asymmetric crypto system. If you want to break that, you have to be able to compute the Eulersche phi function, Euler's phi function, okay? So, but not for 6. You know, we all did that, right? It takes 1 minute. Really long numbers, 2000-bit numbers nowadays, very often. So the question is, how can we do that for very long numbers? Okay? There are 2 ways of doing that. One thing is you do the list here. The problem is, if you have 2000 bits, this list has 2000 entries, and this is, you know, more than the atoms on universe, blah, 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 blah. Okay? That means this brute force approach, simply computing all GCDs, doesn't work if you have to compute 2 to the 2000. Okay, you know, the sun will have cooled down and everything, right? So this is not going to work. The question is, is there any way of computing Euler's phi function quicker? And luckily there is, which is, maybe let's write that down as a question. How can we compute phi of n for large n? Okay, and luckily there's a pretty easy formula for that, which is, answer is theorem 6.3.1 which I think is on the next page in your textbook, hopefully. Yep. Okay. Namely, so it's a little hard to read. We're going to do an example, and then things will be easier so often in life. So you have given is m as an integer, and we happen to have the prime factorization. So we know all the prime factors of m. And this is called the canonical factorization. That means this is the standard form of writing any integer. So all the p1, p2, p3, and so forth, they're pairwise different. So these are all the different prime factors. If you have that, you can compute phi of m with this simple formula, with this uppercase pi symbol here. This großen is p symbol, with this formula. And I'm going to show you an example, okay? So we would really like to know what the phi value of 240 is. One way of doing that is counting stars. We can do that, right? The problem is, now let's say by hand, you have to compute 240 GCD. Enjoy, right? This is no fun. We don't want to do that. The better way is in this formula. The first thing that we do, we write m nicely in its prime factor. So this is 16 times 40, can you do that in your head? 10 times 16 is how much? 160, and then 5 is another half of that, right? 160 plus 80 is 240. So 16 is 2 to the 4 times 3 times 5. This is P1 times E1, P2 times E2, P3, E3. Okay? Das kanonische Primfaktorzerlegung. This is, and 3 is of course 3 to the 1, 5 is 5 to the 1. Okay? So what we're doing now, you plug that into this formula there. What is n in this for 240? What is the value n here? 3, right? That's the number of distinct, also verschiedene Primfaktoren, right? 1, 2, 3. Why do I do distinct if you just, what is the number of prime factors of 240? How many prime factors are in 240? 6. 1, 2, and then 4 times the 2, right? 2 times 2 times 2 times 2 times 3 times 5, right? 6, okay? But distinct prime factors, also einzigartige, they're only 1 to 3. So we run here from 1 to 3, and you do pi times ei minus pi times ei minus 1. Yeah. And then this is not a summation, this is a product symbol, right? The uppercase pi is a product symbol. So this is 2 to the 4 minus 2 to the 3 times 3 to the 1 minus 3 to the 0 minus 4 to the 1 times minus 5 to the 0. Das ist 16 minus 8 ist 8. 3 minus 1 ist 2. Und 5 minus 1 ist 4. Stimmt das? Ja. So this is 2 times 4 is 8. 8 times 8 is 64. Okay? Again, that means if we do this little Gedankenexperiment, if you go down 240, if you actually write 240 GCDs, and you take the red chalk again, die rote Kreide, you would make 64 red stars in that, right? So there would be 64 lines where the GCD is 1, okay? Again, this is much faster. And now, just to jump a little bit ahead, what's going to happen next week, and a lot of people don't know that about RSA. If you want to break RSA, the only thing you have to do, you have to compute phi. If you compute phi, it's just an Euclidean algorithm. It's really boring, okay? So the only thing you have to compute phi. And now there are two cases possible. So you have a number m you have to compute phi of, right? M is unfortunately not 240, it's 200 bits long. Really long number, 600 decimal digits, really, really long number. Now there are two cases possible. The one case is you do know the prime factorization. That means you know that it factors this way, and then you use this formula here. That means if I ask you for the phi value of an integer, you know the factorization, it means you know the p-values here, you simply use the formula. Even for really large numbers, this is easy. Okay, no big deal. This is case one. The attacker in RSA, if you want to break RSA, and you do not know, if you don't know the prime factorization, it's really hard, okay? One thing you can do brute force. It means you have to compute 2 to the 2000 GCDs. Actually, there's somewhat better ways out there, but not much better, okay? And this is at the very heart of the security of your web browser. And certain German bank cards also use RSA, for instance. That it's really hard to compute the GCD if you don't know the Eulersche Phi-Funktion, Euler's phi function, if you don't know the prime numbers. Okay? You always have m is always public, it's part of the public key, everybody knows that, but it's really hard to compute the factorization. If you do know the factorization, it's really easy to compute phi of n. So now I have two little things, and I just show them here on the board. The two other theorems that are important in for RSA, not quite as important, not quite as fundamental. Okay, so there's Fermat's little theorem and Euler theorem, and I just want to show you them here on the wall. Okay. By the way, there's this Fermatsche Theorem or Fermat's last theorem in English. And this is very important, and this has nothing to do with this one, okay? This is called Fermat's little theorem, or in German often der kleine Fermat, okay? So this is not a very deep result. So this tells you, and it's somewhat surprising, if you have an integer a, and you have a prime, if you compute a to the p, so you raise something to the pth power, but everything mod p, the result will be again a. Strange, strange, strange. Okay, so this is 17th century was Fermat. Okay. Blah, 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 blah. That's the first theorem. Okay. The other theorem is a somewhat more general form. Look here. So what we did here is you take a and raise it to the pth power. And now for Euler is more general. What Euler theorem does, you do a, you do modulo m as before, but now you take it not a to the mth power, but a to the phi of the mth power. Okay? So if you have two integers, a and m, and they must be relatively prime, that's a side condition. If you do that, compute a phi to the m, the result is always 1, which is, if you're not used to modular arithmetic, this is a strange thing. We have kind of our feeling tells us you have a, and then you do an exponentiation on a. You would think that this grows and grows and grows and grows. Well, we do know from modular reduction makes it smaller again. But in this case, Euler's theorem tells us that the result is exactly 1. Maybe you can look at an example. So m equals 12, a equals 5, a equals 5. So what do you do here? First we compute phi of 12, which is the formula we saw before. The result is 4. So if you do GCD of 12 and 0, 12 and 1, 12 of 2, you get 4 red stars, okay? And now Euler's theorem tells us a to the phi of m must be 1. Let's look at the result here. A is 5 raised to the phi of 12, so this is 5th raised to the 4th power. It's 25 squared, 625, modulo 12 is 1, okay? So this is what's happening here. It was very fast. Again, we're going to use these results more after the spring break in April. That's it for today. Thank you very much.